Can you hear me now? Can you hear me now? Perfect. Okay, and is the clipboard visible? Excellent. And let me put this up. Can you read the text in the notes? Perfect. I'm going to wait for 2 minutes and begin at 4:05 in case anyone else joins, and then I'll just begin the lecture. Okay, let's begin. So for today, we're going to be looking at similarity, and before I begin the lecture, I need you to recall a couple of things. The first thing to recall is something that we've done in the previous chapter, which is change of basis. And the idea was that if I have a vector space V, which has two different bases, let's suppose basis E, which is V1 to Vn. This basis, ordered basis for this vector space, and another basis F, for example W1 to Wn. Then we discussed how to go between two different bases. More specifically, if we have the standard basis E1 up until En, and if we want to go from, let's suppose, the basis U, which is U1 to Un, if we want to take a vector represented in these, a coordinate vector represented in this ordered basis, and we want to convert it into this basis, the way to do that is to use multiplication by U, where U is called the transition matrix. Which basically means that if your vector is V and it's x1 E1 plus x2 E2 up until xn En, and the way it's represented in the non-standard basis is y1 u1 plus y2 u2 plus up until yn un, then this is the same vector but expressed in terms of the standard basis and expressed in terms of the u1 u1 basis. And the idea was that if you want to go from y to x, then all you need to do is multiply, then x is just found by multiplying u with y, where u was called the transition matrix. Okay? And so if u is your transition matrix, and so what was the vector y and vector x? The vector x was simply the set of coordinates x1 to xn, and vector y was simply y1 to yn. So to go from these coordinates to these coordinates, multiply this vector by u. Let's put a transpose here so that it's more precise. And so x is equals to u, y is the transition matrix. So u was the transition matrix. And if you want to go from x back to y, then y is simply u inverse of x. And over here what you're doing is you're going from the standard basis vector to the non-standard basis vector. And if you recall, then u, matrix u was simply generated by taking these basis vectors as the column vectors of u. So this was u1, this was u2, up until un. And so this was the transition matrix. This is how we go from one basis to another basis, at least from the standard to a non-standard and a non-standard to a standard. And the way to go between two non-standard bases is just to go from one non-standard to a standard and then to a standard to a non-standard. So this was something that we did in the previous chapter. Another thing that we did just last week, or rather in the last lecture, was as follows. What we were trying to achieve in the last lecture was we were trying to look at the matrix representation of linear transforms. And so we were talking about representing L of x as simply a times x. And so these are the two concepts that you need to keep in mind for today's lecture. And so today's lecture asks a question, which is, how do you represent this L if you have different bases to work with? So, for example, if I'm working with the standard basis, then this matrix A will simply be LE1, LE2, and so on. But if I'm working with a non-standard basis, let's suppose I'm working with the bases U1, U2, and UN, then the matrix representation of this linear transformation will be different, and it will actually be a matrix of the sort LU1, LU2, and up until LUN. Right? So this is how you will construct A and this is how you will construct B. But the idea is there's a question on how we will do this. Specifically, keep in mind one important fact, that when you're dealing with this transformation in the standard basis, then input x and output A of x will both be in terms of the standard basis vectors E1 up until En. But if you're working in the non-standard basis, so if you were working with U for the non-standard basis, then input x and output B of x will both be in terms of the basis vectors u1 up until un. And so the question is, can we construct B simply by just putting these vectors as it is? That's the first question. And the second question is, we need to guarantee that the input and output are both being represented in terms of the basis vectors that we're talking about. So B should give an output which should be in terms of these vectors, not in terms of these vectors. Okay? And just to make it clear, what I mean is, if you have x in terms of x1 e1 plus x2 e2 plus blah 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 xn en, then your result ax should also be some alpha 1 e1 plus alpha 2 e2 plus dot 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 alpha n en, if you're in the standard basis. And if you're in the non-standard basis, let's suppose you're in the non-standard basis, that is x is being represented as y1 u1 plus y2 u2 up until yn un. Let's suppose this is the vector that you've taken. Let's call this vector v, let's call this vector av, let's call this vector v. And so if you've represented it like this, actually this was, yeah, let's just keep this as x and this as ax and this is y and this is ay. And so if you're representing it like this, then it should be beta 1 u1 plus beta 2 u2. This is still a bit imprecise, but we'll clear this out in the following discussion. So beta n un. So both the input and the output, rather this should be b times y, both the input and the output should be in the same basis representations. All right. So here's the idea, which is, the first thing is that the matrix representation, the way you represent L in terms of a matrix, is going to be different depending on the basis that you're choosing. And right now we're going to be limiting ourselves to operators that take vectors from one space back into itself. So we're only talking about linear operators right now. We're not talking about v to w. It's starting from the same space and it's giving vectors in the same space. Okay. So what's the idea? Let's take an example and see if it gives us any hints as to what to do in general vector spaces. And so let's consider this example. I'm going to pause for a couple of seconds just to see if you have any questions. Any questions on what I've said so far? So let's suppose we're taking this example where we have a linear transformation that is going from R2 to R2. And so the transformation is that if you have a vector x which has two components, x1 and x2, the first component of the result is 2x1 and the second component is x1 plus x2. And so let's do this example over here. So we had the linear transformation Lx was 2x1 x1 plus x2 transpose. So if, let's take an example, if x was equals to the vector 3, 4, then L of x will be, the first component is 2 times x1, which is 2 times 3 is 6, and the second component is the sum of these two, so 3 plus 4 is 7. So this is a linear transformation going from R2 to R2. Okay. So you have this transformation R2 to R2. Okay. And so the question is, the first simple question is, how do we find the matrix representation if we're just talking about the standard basis? And for the standard basis, we know it's easy. It's simply consider what happens to the A will be made up of columns A1 and A2, such that A1 is what happens to the first standard basis vectors and A2 is what happens to the second standard basis vectors. So this is easy to do. E1 is simply 1, 0, and so the transformation of this would be 2 times 1, which is 2, and 1 plus 0, which is 1. So this is the transform. And if I want the transform of E2, this is L of E1. The second standard basis vector is 0, 1. And if I transform it, LE2, then it simply becomes, the first component is twice of x1, twice of 0 is 0. And the second component is x1 plus x2, 0 plus 1 is 1. And so now I have the matrix representation A, which is, this is the first column and this is the second column. So 2, 1, 0, 1. And so now Lx can be represented as AX. Okay. All right. Okay, so that's all well and good. We have this matrix A over here. Same procedure was done. A is given as this. But now the question is, how do we represent it? What's the matrix of transformation if I have U1 and U2? And actually what we'll need to do is the following. Let's suppose we do the following. First, we need to figure out what happens to these basis vectors. Okay. So the question is, we have two new basis vectors where U1 is equals to 1, 1 and U2 is equals to minus 1, 1. You can verify that this is a basis representation for R2 because both of these vectors are linearly independent. Okay. So you can verify that U1, U2 is a basis for R2. Okay, exercise. All right, and so the question is, what happens to LU1 and LU2? What happens when we transform these? Now, of course, if we use the first matrix that we have figured out, if we use the A matrix, we will get LU1 and LU2. So I can just use LU1 equals AU1, which is simply multiplying 2, 0, 1, 1 to the vector 1, 1. And the result is you can simply multiply and find out 2 times 1 is 2, plus 1 is plus 0 is just 2, and 1 times 1 plus 1 times 1 is 2. So this is what happens to U1 under the original matrix A. And secondly, you have LU2, which is equals to AU2, which is again just 2, 0, 1, 1 multiplied by U2 vector minus 1, 1 is equals to, you get minus 2 plus 0, this is just minus 2, and 1 times minus 1 plus 1 is 0. Now this vector, this matrix is 2, 2 and minus 2. But there is one little problem. A was working with the assumption that you are in the standard basis vectors E1 and E2. So the result, whatever result A gives, these results, these are in terms of E1 and E2. These two are in terms of E1 and E2. they're not in terms of u1 and u2. What we need to find is what is their representation in terms of u1 and u2. Okay? Because the matrix of transformation that we were using was the one using the standard basis vectors. So whatever result it will give you, it will also be in the standard basis vectors. So this 2, 2 and minus 2, 0 is actually, if I write it down clearly, it's LU1 is actually 2E1 plus 2E2, and LU2 is actually minus 2E1 plus 2 plus 0 times E2. But I don't want them to be in terms of E1 and E2, I want them to be in terms of U1 and U2. So the next step is to convert it in terms of U1 and U2. And so let's see how we can do that. So at this point we have the problem of taking a vector from E1, E2 and changing the basis to U1, U2. And so at the start of the class I told you that for going from here to here you need the inverse of the transition matrix that takes you from here to here. So from here to here it's easy, it's just U. From here to here you need U inverse. So the idea is U is simply the basis, columns are U1 and U2. This is how you simply construct the transition matrix from a non-standard basis to a standard basis. So I will just write the columns U1 and U2, and let's just look at what these columns were. Columns U1 and U2 were 1, 1 and minus 1, 1. This is the transition matrix U. I want the inverse of this transition matrix, and so I will try to find the inverse, which I will not do. I have it written down. And so the inverse, so if U matrix was simply, the matrix U was simply 2, 0, 1, 1 and minus 1, 1, we can find the inverse. Okay, so it seems like I haven't written the inverse. So question, we need to find the inverse of this matrix. I will ignore that process, but let's assume we have U inverse. Let's suppose you find the U inverse. So you can do that, find U inverse. But the idea is once you have U inverse, you can transform these matrices, these vectors that you had, 2, 2 and minus 2, 0, which were initially in terms of E1 and E2, you can now change them in terms of U1 and U2. And so recall that the first matrix, first vector was L of U1, which was 2, 2. And to convert it from the non-standard basis to the from the standard basis to the non-standard basis, I will apply U inverse. So I will apply U inverse, I'll find U inverse and I'll multiply it, and the result that you get is the vector which I have written down over here, which is if you do that process, you get the vector 2, 0. This is the vector that you get. And if you take the inverse and multiply it with LU2, where LU2 was this minus 2, 0, if you multiply it with this, you get minus 1, 1. And so what you have is this 2, 2 has been converted into 2, 0, and the other matrix, other vector minus 2, 0, if you multiply it by U inverse, you get the vector minus 1, 1. And so now this process, this entire process, U inverse LU2, is something that has allowed you to represent the linear transformation in terms of, now notice if you take this entire process, you started off with the basis vectors in terms of U1 and U2, and you've ended up with basis vectors in terms of U1 and U2. So if you have, now I can write this. Consider that U inverse L of U1 was found by L of U1 was simply found by multiplying A with U1. And U inverse L of u2 was found by U inverse A u2. So I can make a matrix out of these two columns. Let's suppose I call my matrix B. The first column is 2, 0. The second column is minus 1, 1. And I can write this entire thing, this matrix, as a matrix vector product. Notice that this is U inverse AU1. So the first column is U inverse AU1, and the second column is U inverse AU2, where you can separate this U1 and U2 as a matrix. So it was U inverse A, U inverse A being multiplied by, essentially, if you separate this, you can actually just write it down as U inverse times A, first column, and U2, second column. So this was actually just U inverse A U. So you've written B is equals to U inverse A times U, where B is the matrix representing L with respect to U1 and U2. All right. So let me just go through the entire process one more time, which was that we started off by first considering it in terms of E1 and E2, and this is easy to do. This matrix transformation for E1 and E2 is easy to find. You can represent A just as put 2, 1 in the column and 0, 1 in the column, and you're done. Okay. But if you want to do it for this basis U1 and U2, you first need to find out what happens to them under L, under this A matrix in the standard basis. You find that that result is 2, 2 minus 2, 0. And now the next thing that you need to do is convert these vectors in terms of the non-standard basis vectors. And to do that, you need the transition matrix to do change of basis. So now you're changing basis from standard to non-standard, so you need this U inverse. For this, I just need to multiply 2, 2 by the U inverse, you get 2, 0. And you multiply minus 2, 0 by U inverse, you get minus 1, 1. And now you can make the transition matrix B, which is 2, 0 minus 1, 1, which is the matrix representing L with respect to this non-standard basis U1 and U2. Okay. And so the relationship that we found was B was equals to U inverse AU, where B is the matrix that represents this transformation in this basis, A is the matrix that represents the transformation in the standard basis, and U is the transition matrix from the non-standard to the standard basis. Okay. Let me know if you have any questions with this. No questions? Okay, let's move on. So we have this nice little theorem that tells us that if you have two different bases for your vector space and you have a transformation, linear transformation from V to V, and you have S as the transition matrix. So to go from F to E, you can multiply vectors which are represented in terms of this basis. If you multiply it with S, you will get the coordinates of the same vector but in the different bases. So S is your transition matrix. If you have A, matrix A, which represents this transformation in terms of E, basis E, and if you have matrix B, which represents this linear transformation with respect to the basis F, then you have the fact that B is equals to S inverse times A times S, which is something that we did just now, that you can find B by just multiplying U with A and then multiplying A with U inverse. So that's the relationship, and it doesn't just hold for standard basis vectors, it holds for general vector basis as well, non-standard basis vectors as well. Okay, and so the idea is we can prove this as well. Proof is quite simple to do. Let's go through that proof right now. So let's prove this theorem. So we had vector space E, we had vector space F, we had, these are not two different vector spaces, this is vector V and vector V, okay, and you had L which was taking vectors from V to V. Now these vectors can be represented in terms of basis E, which is V1 to Vn, or they can be represented in terms of basis vectors W, which is this Wn. Okay, and so let's suppose we take this vector. Let's suppose let X be a vector in Rn such that I can write a vector V, small v, which belongs to this vector space, and I write V as x1 W1 plus x2 W2 plus xn Wn, which is basically the representation of any vector in V space in terms of the basis F. So what we're essentially saying is X is the coordinates of V with respect to F. So define the following. We define y is equals to s of x, s times x, t equals to a times y, and z equals to b times x. So what we're essentially doing is we're saying, notice that S was the transition matrix from F to E. So it basically, X was being represented in terms of F and Y will be represented in terms of E. So Y, the vector Y is the coordinates of the same vector V, but in terms of this different basis E. Okay. And what are these two equations saying? Well, equation T is representing this linear transformation. A was L represented in terms of E. So input was represented in terms of E and the output will be represented in terms of E. and consider B, which is L represented with respect to F. So if you take the vector V and represent it in terms of the basis F, the coordinates will be X, and if you multiply it with B, you will get the same transformed vector. So what essentially is happening is, you draw this diagram, is you had this vector V, where V can be written as, where X is VF and Y is VE. It's the same vector but different coordinates because you're using different bases. The vector is the same. If you map this by L onto L of V, then again this vector is in this space, but it can be represented two ways. If you represent it in terms of basis vector F, then it's just C equals to L of V represented in terms of F. But if you represent it in terms of basis vectors E, then it will be just, the coordinates will then be T equals L of V, but now in terms of E. This is, all of this is the same vector, it's just coordinates are different depending on the basis that you've chosen. This was basis F and this was basis E. Okay, and so this will be done by multiplying with B, and this will be done by multiplying with A. So this is B times X and this is A times X. B times X and this is A times Y. Okay, so let's continue the proof. The proof is as follows. We consider simply, just consider the following. If I want to switch between these two Z and T's, then it's clear that S inverse of T will give me Z, because T is the representation in terms of basis E and Z is the representation in terms of basis F. So to go from F to E, you need S, and if you want to go from E to F, you would need S inverse. Okay, so written down, T was the representation of L of V in terms of E, and Z was the representation of L of V in terms of F. So if you want to go from these coordinates, E coordinates, to F coordinates, from F to E you just multiply by S, from E to F you just multiplied by S inverse T. So this is something important that we'll use. Z is equals to S inverse T. And now the proof is quite simple. We just start off by considering what is S inverse A S times X. Okay, so we need to talk about this. Now if you recall, S times X was simply Y. So I can replace S times X by Y. Then if you recall, A times Y was simply T. So A times Y can be represented by T. And S inverse T is something that we just discussed, that S inverse times T is nothing but Z. So S inverse T is Z, and C is nothing but B times X. So I can represent Z, I can replace Z by B times X, where B was the matrix representing linear transformation in terms of the basis F, right? So we get S inverse AS X is just B times X. And so you get the relationship P equals S inverse AS, and that's something that we were trying to prove. Okay, and so that's the simple proof of this statement. You start off from this line S inverse AS, replace Sx by Ay, replace Ay by T, replace this by Z, and Z is just use the relationship Px, and you get this proof that P is the same as S inverse A times S. Which brings us to the definition of similarity. We say that two matrices are similar if you can say that B is similar to A if you can write B as some S inverse multiplied by A multiplied by S. So if the definition is saying following: if you have matrix T and matrix U, then T is similar to U if you can find some matrix, let's suppose L, such that T can be represented as L inverse times U times L. And this is the definition of two matrices being similar. And of course this is a symmetric definition, because if T is similar to U, then I can take these matrices on the other side and I can say L T L inverse is equals to U. And so this definition, I can write U as L T L inverse, which can of course be written as L inverse inverse T times L inverse. So if I consider this to be, let's say, V, so this becomes V inverse T V, where I let V to be equals to L inverse. So if I just replace L inverse by V, it's nothing but U, and this is nothing to say. So T is similar to U implies U is similar to T. So it's a symmetric definition. If one is similar to the other is also similar to the first one. Okay. So A and B are n by n matrices are said to be similar if there exists a non-singular matrix S such that B is equals to S inverse AS. And if A is similar to B, then B is also similar to A. Okay. I'll take a little break and then I'll continue with the example, and I think that that's the last thing for today. Short lecture today. So we just have this differentiation operator, which we'll do. Let me know if you have any queries. Okay, so let's go through the example. D is the differentiation operator on P3. P3 are the polynomials of degree less than 3, which means they are quadratic polynomials or polynomials which are lower degree than quadratic. So we want, if there is a differentiation operator on P3, we want to represent this linear transformation. Differentiation is linear transformation, and we want to transform such that we want to represent differentiation on polynomials of this vector space, and we want to represent them using some matrices. So the idea is that we want to represent differentiation of matrices, differentiation of polynomials of degree less than 3 using a matrix multiplication. So this is quite interesting because differentiation of degree 3 polynomials is being converted into a matrix multiplication, right? And which is a strange thing to do, but perhaps we can have an idea of what we are trying to achieve. So for example, if I have the polynomial, let's suppose P3, let's suppose there is a polynomial P such that it's 4x squared minus 2. If I differentiate this polynomial, this is simply 8x plus 0 if you differentiate it. Now I can write this in terms of vectors where I choose the standard basis vectors. Let's suppose the vectors that I'm choosing is the constant, the linear vector, and the quadratic vector. Then this can be written as minus 2 times 1 plus 0 times x plus 4 times x squared. And so now you've written this polynomial as a vector, the first component being minus 2, the second coordinate being 0, and the third coordinate being 4. Okay, and so if you differentiate it, it becomes 8x, and 8x can again be represented using these 3 basis vectors. There is no constant, so 0 times constant. There is one linear term, which is 8 times x, and there is no quadratic term, so this is 0x squared. And so I have represented the result of this linear transformation. So 4x squared minus 2 was mapped onto 8x using D, and in terms of coordinates, minus 2, 0, 4 was mapped onto 0, 8, and 0. And since we know that differentiation D is a linear operator, we can actually represent this differentiation in terms of some matrix multiplication. So I can see that if this is a vector, maybe I can find a matrix A such that when I multiply this matrix with x, I can get this vector 0, 8, 0. So the goal is to try to find this, and we can do it in the standard basis, which is 1x and x squared, or we could do it in some non-standard basis as well. And so that's the question of this example, is that represent it in terms of the standard basis vectors and represent it in terms of the non-standard basis vectors as well. So standard basis vectors is easy to do. Let's tackle that problem first. Let's suppose we have these standard basis vectors. All we need to do is figure out what happens to the standard basis vectors under this rule. So we know that we can make B is basically representing P3 to P3 in terms of the basis vectors 1, x, and x squared. So of course the idea is simple. For standard basis vectors, you need to do nothing, but you need to find what happens to the first standard basis vectors, the second standard basis vector, and the third standard basis vector under differentiation. So vectors now are these polynomials. This is a polynomial, this is a polynomial, this is a polynomial, and we're trying to figure out what happens to this under differentiation, this under differentiation, and this under differentiation. And so here it is. If you differentiate the constant 1, then the differential is just 0, and to express it in terms of these basis vectors, it's just 0 times 1, no constant term, no linear term, no quadratic term. Similarly, the derivative of x is going to be 1. which is 1 times the constant term plus no linear term plus no quadratic term. And finally, if you differentiate x squared, you get 2 times x, which is there is no constant term, twice of the linear term plus no quadratic term. So this is what happens to the standard basis vector 1, this is what happens to the standard basis vector x, and this is what happens to the standard basis vector x squared, and they are represented in terms of the standard basis vector. So this is vector 0, 0, 0, the coordinates are this is 1, 0, 0, and this is 0, 2, 0. And so if I construct matrix P, it is very simple. D1 is simply 0, 0, 0, then d of x is 1, 0, 0, and d of x squared is 0, 2, 0. So this is how you differentiate. And maybe we can even test this. If I can try to test it, maybe if I multiply 0, 1, 0, 0, 0, 2, 0, 0, 0 with this vector over here, let's try to do this. If I multiply this with minus 2, 0, 4, let's see what vector do I get. So 0 times minus 2 is 0, 0 times minus 2 is 0, 1 times 0 is 0, 0 times 4 is 0. So the first component is 0, second component 0 times 0, 0, 0 times minus 2, 0 times 0, 2 times 4, which is 8, and 0 times 0, 0 times 0, and 0 times 0. So if you have 4x squared minus 2x, 4x squared minus 2, or minus 2 plus 4x, the result is going to be, this is basically saying that the derivative of 4x squared minus 2 is 8x. You've converted differentiation, sorry, this was all invisible. You've converted differentiation into matrix multiplication. So I see that this wasn't visible. Let me just repeat what I said. This was the matrix that we found using this process. And if I multiply B with this vector, we get 0, 8, 0. Okay, so this is the matrix representing differentiation for polynomials which are of degree 3 or less than 3. Sorry, degree less than 3. Okay. All right, so let's go back. And so same thing again, which is that this is how you construct matrix P. You differentiate what happens to each of the standard basis vectors, and then you just write these vectors as columns. So this is 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, and 0, 2, 0, which is 0, 2, 0. And that's simply B. We have found B, which represents this differentiation in terms of the standard basis vectors. Now let's try to do the same process, but for the non-standard basis. So the non-standard basis that we are using this time is, the non-standard basis is, we have first basis vector is the constant vector same, the second one is twice of the linear factor, and the second one is 4x squared minus 2. And so now we are taking this non-standard basis. So my new basis that I'm using is 1, 2 times x, and 4x squared minus 2. And the question is, what happens to, again, we want to construct matrix A. If we're constructing matrix A, we need to see what happens to the first basis vectors, the second basis vector, and the third basis vector. But now this time we have to ensure that we're representing everything in terms of these basis vectors. So if I have the matrix T, if I just take this basis vector 1, and if I differentiate it, the differential is 0. And so in terms of the basis vectors, it's simply 0 times 1 plus 0 times 2x plus 0 times 4x squared minus 2. So the result is simply 0, 0, 0. If I differentiate 2 times x, then the result is 2 which I can represent by 2 times 1 plus 0 times 2x. There is no linear function, and I can just make this quadratic function to be 0 as well. And lastly, if we differentiate 4x squared minus 2, then the derivative of 4x squared minus 2 is simply 8x, which there is no constant term, so it's 0 times 1, plus I want to get 8x here, so to get 8x I need to multiply 2x by 4. So this is 4 times 2x, plus finally again set the quadratic factor to be 0. So the matrix A is nothing but 0, 0, 0, first vector 0, 0, 0, second vector 2, 0, 0, and third vector 0, 4, 0. And so this is differentiation, but in terms of these basis vectors rather than the standard basis vectors. So let's go through the notes, and the notes are saying the same thing, which is if I differentiate these basis vectors and then represent them in terms of my non-standard basis vectors, this is the representation I get for A. And so lastly, we can just simply establish a quick relationship between A and B. So B was simply 0, 1, 0, 0, 0, 2, and 0, 0, 0. And the question is, what's the relationship between A and B? And the relationship is simple. It is B equals to S inverse A times S, where S is the transition matrix. So if I go back to the notes, if you have a transition matrix from the non-standard basis to the standard basis, then you can represent, actually I have written this incorrectly, this should be A equals S inverse B to B times S, okay? And so the transition matrix is actually taking vectors from the non-standard basis, which were 1, 2x, 4x squared minus 2, and representing them in terms of the standard basis vectors 1, x, and x squared. And if you recall from your previous classes, this transition matrix is very easy to construct. It's easy to construct by just representing this basis vectors as in terms of these. So 1 can simply be written as 1 times 1 plus 0 times x plus 0 times x squared. 2x can simply be written as 0 times 1 plus 2 times x plus 0 times x squared. And 4x squared minus 2 can be written as minus 2 times 1 plus 0 times x plus 4 times x squared. And so S transition matrix is very easy to construct. It's just this one, 1, 0, 0, 0, 2, 0, and minus 2, 0, 4. And so the relationship between A and B is simply A equals S inverse B to S, where we're using the theorem where, if you recall, this is the theorem that we're using. The theorem is that if you have two bases, different bases, and you have matrices that represent the linear transformation in one basis and another transformation in another basis, it's the same transformation but in two different bases, then the relationship is B equals S inverse AS, where S is the transition matrix from F to A. Okay, and so over here the roles of A and B have been reversed. Over here A was actually the one which was representing the non-standard basis. So to go from the non-standard basis, A is basically S, matrix S that we've constructed takes from A to B. So if S takes from A to B, then we have the other way around, that this becomes the other way around. B and A switch places and we have A equals S inverse BS. All right. And you can, of course, S is easy to invert. This is an upper triangular matrix. You can invert it. And you can verify that if you indeed take this matrix as, you take this matrix S inverse, and if you've taken this A and B, you can check that when you multiply S with B and B with S inverse, you get the same matrix A. So to convert this matrix into this matrix, you can do this multiplication. And of course, A is similar to B. Okay? And that's your chapter 4. You can do the exercises from the books for 4.1, 4.2, 4.3. There is one thing that I have not talked about which was missing from chapter 3, which was the rank nullity theorem. I will cover that in the next class before we move on to chapter 5. I posted a video, but I'm not sure if that video covers rank nullity theorem, so I'll just cover it on my own. And that's the lecture for today. Let me know if you have any questions. There's only 3 people here, or 2 people here, I think. If you have any questions, let me know. If you're watching this video later, then simply let me know on Piazza, or let me know by email if you have any queries about today's class. These notes have been uploaded, and all of these are available on Google Drive. Okay. Perfect. Okay, thank you. Bye-bye.